In this video, we will be doing a lot of nomenclature examples. So what might be a good idea is to pause the video and from the PowerPoint, make sure you have available or maybe even printed out the 4 steps of writing names and formulas for ionic compounds and the 4 steps for molecular compounds. Being able to look at those 2 slides, those pieces of information, as we're going through these examples will be very helpful. So you may want to pause the video and be able to pull up that rule list or those steps so you can look at that while we're going through some of these specific examples. The first type of compounds we're going to be looking at are ionic compounds. And the first kind of subtype of this are very basic ionic compounds. So I want to pick a compound that we already know what the name is. A lot of you are already familiar with the name of this compound, NaCl. But I want to do this to illustrate the rules that we're going to be using as we do and go through some other examples of things. So for this one, first we want to recognize that we're dealing with an ionic compound. How can we tell? Metal. Sodium's a metal. When you look at its position on the periodic table, chlorine's a non-metal. So we're dealing with an ionic compound. What I strongly suggest is whenever you're dealing with an ionic compound, that you take the time and write out what ions you're dealing with. Sodium comes from group 1A. So as we saw before, things in group 1A are going to form positive 1 ions. Chlorine comes from group 7A. Things in group 7A are going to form negative 1 ions. So whenever you have an ionic compound, take the second that it takes and actually write out what those ions are. It may not seem like you really need to for this one, but as we get into more involved examples, you're going to see where that little trick really makes things a lot easier. So now if you're following through the rules of how to name these ionic compounds, first step says name the positive ion. Well, the positive ion is sodium, and we keep the name of the element. Then it says name the negative ion, replace the ending with IDE. So chlorine is going to become chloride. So you're familiar with sodium chloride being NaCl. That's why we wanted to pick this one. You're already familiar with it, but it illustrates the first couple of steps in doing this. So I want to do another one that's similar to this. The one I want to do is K2O. Again, we're looking at an ionic compound. We know it's an ionic compound because I'm dealing with a metal. We look at potassium, it's on the left-hand side of the periodic table. And oxygen is definitely a non-metal. So I'm definitely still dealing with these ionic compounds. So as we're naming this, before we get into that, we want to actually write out the ions that we have. Remember what the subscript 2 tells us. The subscript 2 tells us we're dealing with 2 potassium. So I need to make sure I'm writing these 2 potassium ions down. And I'm dealing with 1 oxygen ion. Well, when we look at potassium's position on the periodic table, it's in group 1A. Things in group 1A are going to have a +1 charge. So each potassium will have a +1 charge. Oxygen lives in group 6A. Things in group 6A are going to have a charge of -2. So now that we've written out the ions, we can actually write out our name, starting with the positive ion. Name the positive ion first, keep the name of the element. So we're looking at potassium. Then it says name the negative element, or name the negative ion. Replace the ending with IDE. So the oxygen here is going to be replaced by the IDE ending, and we're going to get potassium oxide. A couple of things I want you to notice about this example. One, is there anything in the name that tells us directly there's two potassiums? No. You don't want to be using prefixes or Roman numerals. Those mean something very different than what we have here. Okay, so our name is just simply potassium oxide. There's another thing I want you to kind of notice about these two examples that we've done so far. The two examples that we've done so far, you'll notice that there's charge balance that exists in each of these two compounds. And what we mean when we say charge balance is the same total amount of positive charge that we have of negative charge. In the first example with the NaCl, we had +1, -1. That's charge balance, same amount of positive as negative. In the one we just completed, +1 and +1 for a total of +2, -2. We have charge balance in that. In every ionic compound that you're dealing with, you are going to have charge balance. You're going to have the same amount of positive ions as negative ions. Now in the two examples we've done so far, you've started with the formula and have written the name. I want to do an example going the opposite way, because going the opposite way, you got to make sure you're able to go each way. So we started with the formula here, we went to name. Formula to name. I want to do one going the opposite way, starting with the name where you have to write out the formula. And the one I want to do for this is calcium nitrite. First, we're going to recognize that we're still dealing with an ionic compound. Calcium is a metal. Nitride comes from nitrogen. Nitrogen's a non-metal. So here, we really have to think about our ions before we write the formula. When we think about where calcium is, calcium lives in group 2A on the periodic table. That means calcium is going to have a charge of +2. Nitrogen lives in group 5A. Things in group 5A have a charge of -3. So right now, we don't have charge balance. +2 and -3 definitely are not charge balance. Now, you might be thinking, well, could we change that calcium to +3 and have charge balance? And the answer would be, we can't. We can't change that calcium to +3 because that's not what calcium does. Calcium being in group 2A will only form +2 ions. So you may also be thinking, well, maybe if we change that N3- to N2-, we would quickly have charge balance. That also won't work. Nitrogen, being in 5A, can't form a -2 ion. It has to form this -3 ion. So we can't change the charges that we have here. But what we may be able to change is the relative amounts of each of those ions, because we still have to achieve charge balance. So what we're looking to do here is figure out how many of each of them we need to have our sum total of positives equal our sum total of negatives. And there's two different techniques that can get used to do this. One is you can use the idea of least common multiple. If you like that and you're already seeing it, by all means use least common multiple. I'm going to show you the different way least common multiple works, and it's very quick, so if you're seeing it right away, that's fine. But if you can't, let me show you a different way of doing these. It's kind of just by trial and error. You look at what you need more of. Right now I'm at +2 and -3. I'm short positives. So what am I going to do? I'm going to add another positive ion. Now I'm at a total of +4 -3. Now I'm short negatives. So now I'm going to add one of these negative nitrite ions. So now my sum totals are +4 -6. Now I'm short positives again. So what will I do? I will add another positive ion. Now I have charge balance. +2, +4, +6. -3, -3, -6. Sum total of +6, sum total of -6. Now I have charge balance. Now that I have charge balance, I can write my formula for this. So when I write my formula, I'm just counting what I have. This is why writing out the ions is such a good idea. It really simplifies things where you won't make as many mistakes. I have 3 calciums and 2 nitrites. So my formula will be Ca3N2. Notice how I don't put the actual charges in here, just like you didn't put the charges, didn't start up here. We can get at that information as we want, if we want to. We don't have to explicitly show that. So this is our first type of ionic compound. We call these basic or monoatomic ionic compounds. Next we're going to kind of add on a little bit to this. You saw that we were able to name these just with the first and second rule that we talked about in that PowerPoint presentation. What we haven't done yet is we haven't shown any transition metal ions in here. So that's going to be the next piece. So that's what we're going to work on next, are some transition metal ions, because we're going to see we have to have another rule in order to deal with those. And to illustrate that, I want to do 2 examples kind of side by side in parallel so you can see that. CuCl and CuCl2. Now I'm going to start by kind of naming each one just with the rules we've already used. And we're going to see we're going to have a little bit of a problem. But first I'm going to write out ions. Well, I have 1 copper ion here. I don't know the charge yet. When you look at copper on the periodic table, you're going to see it's a transition metal. Transition metals, we don't know the charge right away just from looking at the periodic table. So we're going to have to figure that out. Chlorine, though, we do know chlorine. Chlorine lives in group 7A. So in ionic compounds, chlorine is going to form that -1 ion. We're going to use that information to figure out what the charge on the copper has to be. Well, the charge on this copper has to be, to have any charge balance, +1. There's no other choice but for it to be +1. So if I were to write the name of this, just using the rules we had so far, positive ion first, copper, negative ion second, I'd have copper chloride. Okay. Let's see what would happen on the right-hand side, though. Again, I have 1 copper ion that I don't know the charge of right away. You cannot tell the charge that the transition metal ion has just from looking at it on the periodic table. You have to figure it out from other information you have. Here I have 2 chloride ions. Again, they're in group 7A for a charge of -1 each. So in order to achieve charge balance, I'm at -1, -2. This copper has no choice but to have a charge of +2. So now I'm going to write the name just based upon the rules we talked about so far, and you're going to see we have a problem. Positive ion first, negative ion second. So I'd get copper chloride. And here you see the problem that we have. So far, for each of these compounds, I have the same name. Copper chloride. Copper chloride. That's a problem because these 2 compounds are very, very different. They have different physical properties, things like density, melting point, boiling point, color. They also have different chemical properties. How they react is very different. And so far, we don't have a way of telling them apart. So that's where that third step in writing ionic compounds comes into play. And you only do this for transition metal ions. And that third step says to use a Roman numeral to indicate what charge that transition metal ion has. Here the copper is +1. So I need to use the Roman numeral 1 for that. Let's kind of quickly go through our Roman numerals. Roman numeral 1 is I. Roman numeral 2 is II. Roman numeral 3 is III. Roman numeral 4, IV. Roman numeral for 5 is V. Roman numeral for 6 is VI. Roman numeral for 7 is VII. That's as far as we have to go in terms of our Roman numerals. So this is +1, so I need to use the Roman numeral 1 in order to describe that. Here, the copper has a charge of +2. So I need to use the Roman numeral 2 to indicate that. And it's the use of the Roman numerals and the transition metals that starts to make these a little bit more complicated than the types we did before. It's real easy to mix up what the Roman numeral means. The Roman numeral does not tell you how many coppers you have. That's not the meaning of the Roman numeral. The Roman numeral has the meaning of what is that charge. That the charge is +1. That the charge is +2. It's not how many coppers, it's copper of what charge. That's how this really means. We don't speak it that way. We would just say copper 1 chloride, copper 2 chloride. But what this really means is this is copper chloride of the type that copper has a charge of +1. This is copper chloride of the type that copper has a charge of +2. That's the true meaning of these Roman numerals. And you only do that, use these Roman numerals for the transition metal ions because they have multiple different options. On to another set of examples using these transition metal ions. So next that I want to do, and I'm going to do 2 in parallel again so you can kind of see how this works. FeS and Fe2S3. These are the 2 that we want to work through and do. First, we're still recognizing these are ionic compounds. Metal, nonmetal. Metal, nonmetal. We still have ionic compounds. So when we have ionic compounds, we want to think about charges. What ions are actually present? Here I have a iron ion. I don't know the charge yet though. Can't figure that out just from looking at the periodic table. I do know what's happening with the sulfur though. For the sulfur is in group 6A. So an ionic compound, sulfur is going to form that -2 ion. So now using that idea of charge balance, I know what the charge on this iron is going to be. The charge on this iron is going to be +2. So now I can name this compound on the left. Positive ion first, that's iron, keep the name of the element. Negative ion second, replace the ending with IDE, so the sulfur becomes sulfide. Because iron's a transition metal ion, I must use a Roman numeral to indicate the charge. The charge this iron has is +2. So I need the Roman numeral 2 to indicate that. Remember, I don't have 2 irons. The Roman numeral is telling me what charge the iron has. That Roman numeral is telling us what that charge is. That's the relationship. Now if we do the one on the right hand side. Here I have 2 iron ions. I don't know the charges yet. But I have 3 sulfide ions. Well, sulfur we said was in group 6A. That would be -2 charged. Well, in order to achieve charge balance, I'm at a total of -2, -4, -6. I need to be at a total of +6. So a total of +6, if I have 2 of them going into that +6, that would make each one have to have a charge of +3. That's the only way I could have charge balance is if each iron had a charge of +3. So now I'm ready to name this. Positive ion first, keep the name of the element, that'll be iron. Negative element second, replace the ending with the IDE ending. And now because iron is a transition metal ion, I must use a Roman numeral in order to indicate its charge. And the charge the iron has, we don't list the total charge. We list what type of iron we're dealing with. It's iron that has what type of charge? The type of charge that the iron has is +3. We're not with the Roman numeral listing the sum total of all the charges. We're saying it's iron of what type, and the type is +3. So this is how you use Roman numerals. You must use Roman numerals when you have those transition metal ions because they can have multiple different charges. We need to have a way of distinguishing these compounds apart from each other. So we just did some examples of going from formula to name. I want to do one example going the reverse way with you, where we start with a name and we're going to write a formula from that name. So the one I want to do with you is we're going to write the formula for titanium 4, IV 4 phosphide. So I have titanium 4 phosphide here. Well, ionic compound, metal, non-metal. So let's go ahead and work on our formula for this. So titanium is Ti. Now just from its position on the periodic table, I don't know what the charge is from the periodic table. But the name is actually telling me what charge this has. IV is 4. What that Roman numeral is telling me that is I have titanium of the type that has a +4 charge. Phosphide comes from group 5A. We said things in group 5A have a -3 charge. So here are the ions I'm dealing with. Titanium +4, phosphide 3-. Well, I need to achieve charge balance. So again, you can do this through least common multiple or trial and error. I'm going to show it with trial and error just to show you, if you're not comfortable with least common multiple, that there's another way. +4 -3, well, I'm short negatives. What can I do? Tack on a negative. Now I'm at +4 -6. I'm short positives. I need to tack on a positive. +8 -6. Now I'm short negatives again. Now I need to tack on a negative. +8 -9. Now I'm back to being short positives. Tack on another positive. +4 +8 +12. -3 -6 -9. I'm short negatives again. Let me tack on a negative. Check to see if I have charge balance. +4 +8 +12. -3 -6 -9 -12. I have charge balance. That means this is the correct number of each of the type of ions that I'm dealing with. I'm now ready to write my formula. I have 1, 2, 3 titaniums and 1, 2, 3, 4 of the phosphide. So I'm looking at a final formula of Ti3P4. Charge balance still works whether you have transition metal ions or not. That doesn't end up going away from that. So I'm going to show you one going in this opposite direction because you want to make sure you're able to go in each direction. You want to make sure you can take a name, go to a formula. You want to make sure you can take a formula and still be able to name it. And writing out the ions so you can be looking at them really helps each of those things happen. The next still dealing with ionic compounds, but the next thing we want to work with are what's called the polyatomic ions. Those polyatomic ions, there's no way around it but to memorize them. But what a polyatomic ion is a polyatomic ion. So if we were to define a polyatomic ion, it's a group of atoms that, as a group, have an overall charge. So it's a group of ions that, as a group, have an overall charge. And there's no way around this. You have to. This is a must. In your book, there's a table of the names and the formulas of the polyatomic ions. There's no way to be able to do nomenclature without knowing those names and formulas. You just have to memorize those. And in general, the sooner you memorize those, the better, because they won't be constantly causing you trouble. Best way to memorize them, flashcard. If I take one of them as an example, on one side of the flashcard you might have the formula, CO3 2-. This 2- belongs to that whole collection of atoms. So this would be one side of your flashcard, the CO3 2-, and then on the other side of your flashcard would be the name. CO3 2- is the carbonate ion. And then you would just go through and keep doing those flashcards of all the ones in that table in your textbook until you have them all memorized. There is no other way but to sit down and memorize those. Now that we know what polyatomic ions are, I want to do some examples of nomenclature that actually deal with them. And the biggest thing for the polyatomic ions is they're essentially following all the other rules we've already talked about for the ionic compounds. It just comes down to you making sure you have the names and the formulas memorized. So I do want to do a couple of examples just to show you. The first one I want to do is this one, NaNO3. And the first real thing to focus on when you're dealing with the polyatomic ions is if you kind of play back to that definition I had of a polyatomic ion, the key word in that definition is group. You have to treat those things as a group. They always get worked on as a group. You're not splitting up all the pieces. So here you kind of recognize, hey, that's going to be one of those polyatomic ions. I need to recognize it as that polyatomic ion, not as one nitrogen and 3 oxygens and then split those up. We want to treat these, think about these, and view these as an actual group. So how do we deal with this? This is still an ionic compound, positive, negative. If you're familiar with NO3, you know that's going to have a negative charge. And the only way to do that is to go through and memorize the formulas and the names. So we still split this up. Sodium lives in group 1A for a +1 ion. This, I'm not breaking it down into an individual nitrogen and 3 oxygens. I need to keep it together as a group. That as a group, this collection of NO3 overall has a charge of -1. So that's my negative ion. Really, really critical that you view these polyatomic ions as groups, not, oh, I need to break it down into 1 nitrogen, 3 oxygens. That's not what you're doing. Instead, you're keeping them together. Then, when you name this, kind of the same thing that you've been doing before, you're going to keep doing. Well, name that positive ion. Sodium. Next up talks about naming the negative ion. Well, that rule of keep the element name and replace the ending with ID worked fine for those monoatomic ions. But this special thing, this specific thing, NO3- has a specific name. You just use the specific name for that. NO3-1 we call nitrite. That's why you have to know these formulas and these names for the polyatomic ions. It really is, unfortunately, just rote memorization, but it has to happen. Otherwise, you're not able to successfully name compounds and write formulas for compounds. I want to do another polyatomic ion example. We're not going to do too many of these because they're following the same rules. There's not a lot of new rules for the polyatomic ions other than you having to make sure that you know those specific formulas, charges, and names. But there is one additional thing that we have to do with the polyatomic ions, and I want to do an example of that. The one I've chosen for us, again, goes the opposite way, starting with the name, writing the formula, calcium chlorate. So we're going to write the formula for this. Well, again, we're dealing with an ionic compound. We recognize this is one of the names of one of those polyatomic ions. Calcium is in group 2A, so we know calcium has a +2 charge. This also shows why you must know these names and formulas. If you don't know what chlorate is in terms of its formula and charge, you're kind of stuck on the problem, unable to advance or do anything really before it even started. So that's a really critical requirement that you know these formulas and names. Once you recognize the formula and names, you'll recognize that chlorate is Cl O3 with a -1 charge. Now, just like all the other ionic compounds, this is going to hold true as well. You still have to have charge balance. That never goes away for ionic compounds. +2 -1. So to achieve charge balance, what do I need? I need another one of these negative ions. Now I'm at +2 -2. Now I have charge balance. Now I'm able to write my formula. Positive ion first, negative ion second. And here is where we got to be a little bit careful. I really have 2 of these, but how should I show it? Well, if I put a 2 over here, it's kind of unclear if it's 2 of these or 2 with the calcium. Maybe if I tried a subscript of a subscript, well, that doesn't really help because that could kind of look like 32, and that would be real confusing as well, and that's not what I have. I don't have a chlorine and 32 oxygens. I have 2 of these things. So this is where that last rule for naming ionic compounds comes in. If you have more than one of the polyatomic ion, here I have 2, use parentheses and put the subscript outside the parentheses. And here we're using parentheses just like you do in other subjects. Sometimes you use parentheses in your writing to set aside a specific thought. Sometimes you use parentheses in math for grouping. This now clearly shows that this is the group, ClO3, and then I have 2 of them. So this is going to be our final formula. So really,